Look up at the night sky with me for a moment. Even if you're resting now, eyes closed, you can picture it. Stars scattered across darkness, the Milky Way's pale river of light, maybe the moon, maybe planets, Venus bright near the horizon, Jupiter steady and calm. Everything you see up there, every point of light, every galaxy we've ever photographed, every star that's ever caught your eye. All of it together makes up less than 5% of the universe. 5%. The rest is hidden, invisible, moving through space and through us in ways we're only beginning to understand. This is where we begin tonight, in darkness, in mystery, in the gentle recognition that most of reality is hidden from our eyes. Before we dive in, if you enjoy these explorations of space and our cosmic perspective, a quick like or subscribe would really help this channel grow. But mostly, just stay as long as you'd like. We're not in any hurry. When we look out at the cosmos, we're seeing with light. Our eyes catch photons that have travelled sometimes for billions of years to reach us. Telescopes extend our vision, gathering more light, seeing deeper into space and further back in time. But light can only show us things that interact with light. Stars that shine, gas clouds that glow, dust that reflects or blocks. What if most of the universe doesn't do any of that? What if most of reality is dark? Not because it's far away, not because it's dim, but because it simply doesn't interact with light at all. This is the situation we find ourselves in. We live in a universe where the vast majority of matter is completely invisible. It doesn't emit light. It doesn't absorb light. It doesn't reflect light. It passes through ordinary matter almost as if nothing is there. And yet, without it, galaxies wouldn't exist. Stars wouldn't have formed. We wouldn't be here. We call it dark matter. Not a poetic name, really. Just a description of what we can observe, or rather what we can't. It's matter, because it has mass, because it pulls on things with gravity. It's dark because it hides from every form of light we shine into the cosmos. You're moving through it right now. As you rest, as you breathe, dark matter particles are passing through your body, through the earth, through everything, barely noticing we're here. It's a strange thought, humbling maybe, or perhaps oddly comforting, to know that mystery isn't something distant, reserved for the edges of space. It's here, intimate, closer than we ever imagined. We'll explore this darkness together, gently, letting each idea settle before we move to the next. Let's travel back together. Back to the 1930s, to a time before we knew how vast the universe truly was. Back to a Swiss astronomer named Fritz Zwicky, working at Mount Wilson Observatory in California, pointing his telescope at a distant cluster of galaxies called Coma. Zwicky was studying how galaxies move within clusters, how they orbit around each other, held together by their mutual gravity, like bees swarming around a hive. He measured their speeds carefully, patiently, night after night. And what he found didn't make sense. The galaxies were moving too fast. Imagine watching ice skaters spinning around a central point. The ones closer to the centre move slower. The ones farther out move faster, but there's a limit. Spin too fast and they'd fly away, break free from the circle entirely. Gravity can only hold things together if there's enough mass pulling inward. Zwicky's galaxies were spinning so fast they should have flung themselves apart billions of years ago. They should have scattered into the void like sparks from a fire. And yet there they were, held together, stable, as if something invisible was gripping them. He did the calculations over and over. He measured the visible mass, all the stars he could see, glowing in his telescope. Then he calculated how much mass would actually be needed to hold these galaxies together at the speeds they were moving. The numbers didn't match, not even close. To keep the cluster bound, there would need to be hundreds of times more mass than what he could see. Hundreds of times more matter than all the stars combined. Where was it? Zwicky proposed something radical. He suggested there must be dunkel materie, dark matter filling the cluster. Invisible mass, far outweighing everything visible. providing the gravitational glue that held it all together. Most astronomers at the time didn't believe him. The idea seemed too strange, too convenient. Maybe his measurements were wrong. Maybe he'd miscalculated. Maybe there was another explanation, something simpler, something that didn't require inventing invisible matter. So the idea waited. It sat quietly in scientific journals for decades, largely ignored, while astronomers went about their work studying the things they could see. But the clue was there, the first whisper of something profound. Galaxies were moving through space as if held by invisible hands. We can picture Zwicky on those cold mountain nights, eye pressed to the telescope, watching distant galaxies wheel through the darkness, recording their speeds, sensing something enormous that no one else could see yet. He was patient. He trusted what the numbers told him, even when it led somewhere unexpected. The universe was revealing itself to be stranger than anyone had imagined. Not smaller and simpler as we learned more, but larger, deeper, filled with layers of reality we couldn't directly perceive. And this was only the beginning. The galaxies kept spinning, held by their invisible companion, waiting for someone else to notice, to measure again, to confirm what Zwicky had seen. That someone would come. But first, decades would pass. The mystery would deepen, quietly, in the dark. Let's move forward now, through the decades, to the 1970s, to another astronomer, another telescope, another series of patient nights spent watching galaxies turn. Her name was Vera Rubin. She wasn't looking at galaxy clusters like Zwicky had. She was looking at individual spiral galaxies, beautiful pinwheel structures like our own Milky Way, arms of stars sweeping out from a bright central bulge. She wanted to understand how they rotate, how the outer edges move compared to the center. It seemed like a straightforward question. Most of the visible matter in a galaxy, most of the stars, most of the light, concentrates toward the center. So naturally you'd expect the outer stars to orbit more slowly, the way outer planets in our solar system move more leisurely than inner ones. Mercury races around the Sun. Neptune drifts slowly through its distant orbit. That's how gravity works when most of the mass is in the middle. Rubin measured the rotation speeds of stars at different distances from galactic centers. She used spectroscopy, analyzing how light shifts as stars move toward or away from us. Night after night, galaxy after galaxy, she built up rotation curves, graphs showing how fast stars orbit at each distance from the center. And the curves were wrong. Stars at the outer edges of galaxies were moving just as fast as stars closer to the center, sometimes even faster. The rotation curves stayed flat, stretched out to the very edges of the galaxies, far beyond where most of the visible stars ended. This shouldn't happen. It violated everything we understood about orbital mechanics. Imagine the planets in our solar system suddenly all orbiting at the same speed, regardless of their distance from the Sun. Pluto moving as fast as Mercury. It would mean there's mass we can't see, spread throughout the entire solar system, changing everything. That's what Rubin was seeing in galaxy after galaxy. The rotation curves told a clear story. There's far more mass in these galaxies than we can see, and it's not concentrated in the center. It extends outward, forming a vast halo around each galaxy, holding those outer stars in their impossibly fast orbits. She wasn't the first to notice this. A few astronomers before her had seen hints of it. But Rubin was systematic, thorough. She measured dozens of galaxies, then hundreds. The pattern held every single time. The evidence became undeniable. Galaxies are embedded in dark matter halos, like insects trapped in amber we can't see. The visible galaxy, all the stars, all the light, is just the small, bright center of something much larger. The dark matter halo can extend 10 times farther out, weighing 10 times more than all the stars combined. We float in these halos. Our Sun, our Earth, everything we know orbits through the Milky Way's dark matter halo right now. particles streaming past us, invisible, unfelt. Rubin faced skepticism, as Zwicky had. Some colleagues suggested alternatives. Maybe our understanding of gravity was wrong at large scales. Maybe there was gas or dust we couldn't detect. Maybe. But she kept measuring, kept observing, kept presenting the data, calm and steady. She once said that she became an astronomer because she loved the night sky. There's something beautiful in that. How wonder led to discovery, how looking up with curiosity revealed one of the universe's deepest secrets. The galaxies told her their truth, and she listened. By the end of her career, dark matter had shifted from a fringe idea to an essential part of cosmology. Not because anyone had seen it directly, but because its absence made no sense. The universe simply didn't work without it. The rotation curves were a kind of shadow, the outline of something invisible, traced by its effects on everything around it. And those shadows were everywhere, so we have this mystery, invisible mass, filling the universe, holding galaxies together. The natural question, the one scientist asked immediately, was simple: what is it? Before we can understand what dark matter is, it helps to walk through what it isn't. Sometimes elimination brings us closer to truth. Sometimes the process of setting aside wrong answers teaches us as much as finding the right one. Let's sit with each possibility for a moment, gently, and see why each one falls away. Maybe it's just regular matter that happens to be dark. Clouds of cold gas drifting between stars too cool to glow. We know such clouds exist. Molecular hydrogen, cosmic dust, spread through galaxies like fog. But we can detect these clouds in other ways. Radio telescopes can see them. They block background light, creating dark patches. We've mapped them throughout our galaxy, and when we add them all up, there isn't nearly enough to account for the missing mass. Not even close, so it's not gas or dust. What about objects that don't shine? Planets, asteroids, failed stars called brown dwarfs. Things made of ordinary matter but too small or cold to emit much light. Astronomers even gave these hypothetical objects a name: machos, massive compact halo objects. For a while, this seemed promising. Maybe galaxy halos are filled with countless dark, Jupiter-sized objects, invisible individually, but adding up to enormous mass. Scientists tested this idea using gravitational lensing. When a massive object passes in front of a distant star, its gravity bends the starlight, making the star briefly brighten. A cosmic magnifying glass effect. If machos filled our galaxy's halo, we'd see these brightening events regularly as they drifted past background stars. They searched for years, monitored millions of stars, found some lensing events. Yes, but nowhere near enough. Maybe machos account for a small fraction of dark matter, but they can't be the main answer, so it's not dark planets or brown dwarfs either. Black holes then, invisible by definition, massive, scattered throughout galaxies. Black holes do exist, certainly, but they're not invisible to everything. Matter falling into a black hole heats up tremendously, radiating X-rays before it crosses the event horizon. A galaxy filled with enough black holes to explain dark matter would be blazing with X-ray emissions. We don't see that, and black holes form from dying stars. There's a limit to how many there could be based on star formation history. The numbers don't work, so not black holes. What about neutrinos? These are real particles, barely interacting with anything, flooding through the universe in incomprehensible numbers. Every second, trillions pass through your body without you noticing. For a while, neutrinos seemed like perfect dark matter candidates. Invisible, abundant, barely interacting with normal matter. But there's a problem. Neutrinos move too fast, close to the speed of light. They're hot dark matter, streaming through space too quickly to clump together and form the structures we see. Computer simulations show that if dark matter were made of neutrinos, galaxies wouldn't form the way they do. the universe would look fundamentally different. Dark matter has to be cold, moving slowly enough to gather in halos to provide stable gravitational scaffolding, so not neutrinos either. One by one, we've eliminated the obvious answers. Dark gas, dark objects, black holes, known particles, none of them fit. What remains is stranger. Dark matter appears to be something else entirely. Not ordinary matter made invisible, but a different kind of matter. Something that exists alongside everything we know, filling space, providing mass and gravity, but interacting with our world only through that gravity. It's like discovering there's been someone sitting beside you all along, in a chair you couldn't see, in a room you thought you knew completely. The universe is layered, and we're only just beginning to perceive the layers. Let's pull back now, all the way back, beyond our galaxy, beyond our local cluster, out to the larger scales we can observe. When we map the universe, when we plot the positions of millions of galaxies across billions of light years, a structure emerges, not random, not uniform, something beautiful and strange. Galaxies gather into clusters. Clusters link together in long filaments, like bridges spanning the void. These filaments connect at nodes where thousands of galaxies congregate. And between these bright strands there are voids, vast empty regions, hundreds of millions of light years across, containing almost nothing. It looks like a web, the cosmic web, astronomers call it, or sometimes a sponge, foam, the structure you'd see if you could freeze sea foam and look at it closely. This is the largest structure in the universe, the pattern that emerges when you step back far enough to see the whole canvas, and dark matter created it. Let's go back to the beginning, back to the early universe, about 380,000 years after the Big Bang. The universe was nearly uniform then, hot, dense, filled with hydrogen and helium gas, energy and light mixed together in a glowing fog, but not perfectly uniform. There were tiny fluctuations, quantum ripples from the earliest moments, small regions where matter was slightly denser than average. These denser regions had slightly stronger gravity. They began to pull matter toward them. But the process was slow. Ordinary matter was still too hot, too energetic, radiation pressure pushing against gravity's pull. Dark matter, though, didn't interact with radiation. It didn't feel that pressure. It could begin collapsing immediately, gathering in the denser regions, building up mass. Dark matter fell first. It clumped together over millions of years, creating gravitational wells, valleys in the fabric of space-time. And then later, when the universe cooled enough, ordinary matter followed, falling into those wells like water finding low ground. The first stars formed in dark matter halos. The first galaxies assembled where dark matter had gathered. Every galaxy we see today sits nested in its dark matter cradle, held and shaped by that invisible presence. On larger scales, dark matter continued structuring the universe. It pulled galaxies together into clusters. It stretched those clusters out into filaments, connecting dense regions while leaving the voids nearly empty. If you could somehow remove all the normal matter, all the stars, all the gas, everything visible, the dark matter structure would remain. The cosmic web would still be there, invisible but intact. Galaxy clusters would be dark matter clumps. Filaments would be dark matter bridges. The scaffolding would stand even without the building. We can map this scaffolding, not by seeing dark matter directly, but by watching how its gravity affects light from distant galaxies. We see how light bends around invisible mass. We see how galaxy motions trace the underlying dark matter flow. Computer simulations let us watch this structure form. Starting from the early universe's tiny fluctuations, we can fast forward through billions of years, watching dark matter clump and gather, watching the cosmic web emerge naturally from gravity and time. The simulations match what we observe remarkably well. The size of the filaments, the emptiness of the voids, the way galaxies cluster, it all appears in the models when we include dark matter. Remove dark matter from the simulations, and the structure falls apart. The universe looks nothing like what we see. So we live in a structured cosmos, not chaos, not simple uniformity, but something in between, organised at the larger scales by invisible architecture. The cosmic web holds us. Our galaxy hangs in a filament, connected to other galaxies through dark matter's gravitational threads. We're part of a larger pattern, a structure so vast it spans observable space. It's grounding, in a way, to know there's order at these immense scales, that even in the vastness there's connection, organisation, threads linking everything together. The darkness isn't empty, it's the framework upon which everything else rests. There's something almost magical about gravitational lensing. It's the closest we come to actually seeing dark matter. Not the matter itself, but its fingerprints, its presence revealed through one of the universe's most elegant phenomena. Let me explain it gently. Einstein taught us that mass warps space-time. Imagine space-time as a fabric, stretched out smooth and flat. Now place something heavy on it. A star, a galaxy, a clump of dark matter. The fabric curves around that mass, creating a depression, a well. Light always travels in straight lines through space-time, but when space-time itself is curved, those straight paths bend. Light from a distant galaxy, travelling toward us, passes near a massive object along the way. The light follows the curve of space-time bending around the mass. From our perspective, the distant galaxy appears distorted, sometimes stretched into an arc, sometimes smeared into a ring, sometimes split into multiple images, the same galaxy appearing in different places in the sky. This is gravitational lensing, mass acting as a cosmic lens, bending and focusing light. And here's the beautiful part. It doesn't matter what kind of mass. Visible matter lenses light. Dark matter lenses light exactly the same way. Gravity is gravity, whether we can see the source or not. So we can map dark matter by watching how it bends light from galaxies behind it. Look at images from the Hubble Space Telescope, deep field observations of distant galaxy clusters. You'll see arcs everywhere, streaks of light curving around the centre of the cluster. Distant galaxies, their light warped by the cluster's gravity as it passes through. Astronomers can analyse these distortions carefully, measuring exactly how much the light has bent, mapping where the mass must be to create that pattern, and when they do, they find far more mass than the visible galaxies contain. The dark matter halo reveals itself. We can see its shape, its distribution, traced out by the bent light from beyond. Some of the most striking examples come from colliding galaxy clusters. When two clusters merge, the galaxies pass through each other mostly unscathed. Space is so vast that stars rarely collide. The gas between galaxies does collide, heating up, glowing in X-rays, slowing down from the impact. But the dark matter, it doesn't collide at all. Remember, dark matter barely interacts with anything, even with itself. So the dark matter halos pass through each other like ghosts, continuing forward while the gas gets left behind. We can see this separation. X-ray observations show where the hot gas is. Gravitational lensing shows where the mass is, and they're in different places. The mass, the dark matter, has moved ahead, separated from the visible matter. The Bullet Cluster is the most famous example. Two galaxy clusters that collided billions of years ago. The X-ray glow marks where the gas stopped. But gravitational lensing reveals that most of the mass kept moving, pulling forward, invisible. It's one of the strongest pieces of evidence for dark matter's existence. Something is there, bending light, creating gravity, but it's not the gas, not the stars, not anything we can see directly. We're watching the invisible become visible through its effects. There's something profound about this. We can't touch dark matter, can't photograph it, can't catch it in a jar. But we can see its influence, written across the cosmos in bent light and distorted galaxies. It's like seeing wind through swaying trees, knowing rain has fallen by seeing wet pavement, understanding presence through absence, through effect, rather than direct observation. The universe has given us this gift, gravitational lensing, a way to perceive what would otherwise remain completely hidden. Einstein's equations become our eyes, light becomes our messenger, and curved space-time becomes the canvas where dark matter paints its portrait. Every warped galaxy, image, every Einstein ring, every arc of light is a reminder. There's more here than meets the eye. Reality has layers. The invisible is real, and we can see it if we know how to look. Deep underground, beneath mountains and ancient rock, in some of the quietest places on Earth, scientists are waiting in the dark. They're listening for something that might never come. A whisper, a single interaction, the faintest touch of a particle that barely knows our world exists. They're hunting for dark matter. Let's go down there together, down into the mines, the caverns, the laboratories, buried under thousands of feet of stone. Why underground? Because dark matter particles, if they exist as particles, are extraordinarily shy. They pass through ordinary matter almost as if it isn't there, through the earth, through rock, through detectors, through us. Trillions of them every second, and they notice nothing, interact with nothing, almost nothing. Theoretically, very rarely one might collide with an atomic nucleus. A dark matter particle, drifting through a detector, might strike an atom and transfer a tiny bit of energy. It would be an incredibly subtle event, like throwing a ping-pong ball at a mountain and having it bounce back. But if you could detect that bounce, that tiny recoil, you'd have direct evidence of dark matter. The problem is noise. Cosmic rays constantly rain down from space, hitting detectors, creating false signals. Radioactivity from the rock around us, from the detector materials themselves, generates background events that could mask a real dark matter interaction. So scientists go deep, a mile underground, sometimes more. The rock above filters out cosmic rays, absorbs most of the interfering particles. Down there, in that ancient silence, the background noise drops away. What remains are chambers filled with extraordinarily sensitive detectors. Some use liquid xenon, cooled to extreme temperatures, waiting for a dark matter particle to bump an atom and create a flash of light. Some use crystals of germanium or silicon, so pure and cold they can detect the heat from a single atomic recoil. Some use tanks of liquid, argon, of supercooled water, each with their own way of listening. The detectors sit in the dark, shielded, isolated, recording. Days pass, weeks, months, years. Scientists watch the data, searching for the signal that would change everything. A pattern of recoils consistent with dark matter particles streaming through the detector from a specific direction, varying with Earth's motion through the galaxy's dark matter halo. It's an exercise in patience, in faith, almost. Spending careers building detectors for something that might not interact the way we think, might not exist as particles at all, might remain forever beyond our reach, and yet they continue. Each generation of detectors more sensitive than the last, ruling out possibilities, narrowing the search, pushing into unexplored territory. There's something beautiful about it. The dedication, the willingness to sit in darkness, literally and figuratively, waiting for nature to reveal herself. Some experiments are in old mines, converted salt mines, abandoned gold mines, deep iron mines, the Sudan mine in Minnesota, the Sanford Underground Research Facility in South Dakota, nearly a mile beneath the Black Hills, Gran Sasso in Italy, under the Apennine Mountains. Others are under ice. Ice Cube at the South Pole uses the Antarctic ice sheet itself as a detector, watching for neutrinos and other exotic particles. Each location chosen carefully, each detector designed with exquisite precision. The scientists who work on these experiments often do so for decades, entire careers spent refining techniques, reducing background, waiting for a signal. So far, no confirmed detection, no definitive ping from a dark matter particle, just increasingly stringent limits on what dark matter could be, if it exists as we imagine. But absence of evidence isn't evidence of absence. Dark matter could interact even more weakly than our current detectors can sense. It could be there, passing through just beyond our reach. Or perhaps we're looking for the wrong thing entirely. Perhaps dark matter isn't a particle we can catch this way. The search continues regardless. New detectors come online, new techniques emerge, the sensitivity improves, and in those deep, quiet places, the waiting goes on. There's something humbling about it, something that speaks to our persistence as a species, our need to know, to understand, to reach toward mysteries even when they don't reach back. The darkness underground mirrors the darkness of space, both holding secrets, both waiting, patient, for us to learn how to listen. So what are they looking for exactly? What kind of particle could be dark matter? The truth is, we don't know. But we have ideas, theoretical possibilities, each with its own character, its own way of hiding from us. Let's meet them, these phantom candidates, gently, one at a time. First, the most popular candidate for many years, WIMPs, weakly interacting massive particles. The name tells you almost everything. They'd be massive, heavier than protons, maybe 10 times heavier, maybe 100. And they'd interact weakly, through what physicists call the weak nuclear force, the same force responsible for certain types of radioactive decay. WIMPs are appealing because they emerge naturally from certain theories in particle physics, theories that extend the Standard Model, our best description of fundamental particles. In particular, a framework called supersymmetry predicts particles that would have exactly the right properties to be dark matter, and there's an elegant coincidence called the WIMP miracle. If you calculate how many WIMPs would have been produced in the early universe, then calculate how many would survive to today, after annihilating with each other, you get roughly the right amount to explain dark matter. It's suggestive, perhaps too convenient to ignore, but we haven't found them. Decades of searching, detectors getting more and more sensitive, and no WIMP has announced itself. The parameter space keeps shrinking. WIMPs, if they exist, are shyer than we thought. Then there are Axions. These are completely different. Incredibly light particles, billions of times lighter than an electron. So light they'd behave almost like waves rather than particles, rippling through space. Axions were originally proposed to solve a different problem in particle physics, something called the strong CP problem. It's technical, arcane even, but the solution, the axion, happens to have the right properties to be dark matter. If axions are dark matter, they'd be everywhere, forming a kind of quantum field permeating space. Not individual particles you could catch, but a collective wave, an invisible ocean we're swimming through. Scientists search for axions differently than WIMPs. They use devices called haloscopes, essentially very sensitive radio receivers, tuned to detect the faint electromagnetic signals that might arise when axions convert to photons in strong magnetic fields. Again, no detection yet. But axions remain a strong candidate. The search continues across different frequency ranges, different possible axion masses. There are other possibilities, more exotic, stranger still. Sterile neutrinos, particles that don't interact through any of the known forces except gravity. Complete ghosts, even more invisible than regular neutrinos. Primordial black holes, not from dying stars but formed in the early universe from density fluctuations. If they're small enough, numerous enough, they might make up dark matter without contradicting our observations. Self-interacting dark matter, particles that ignore ordinary matter but interact with each other, creating dark matter dynamics we're only beginning to explore. Fuzzy dark matter, ultralight particles that form wave-like structures on galactic scales, potentially solving certain puzzles about how galaxies form. Each candidate has advocates, research programs, predictions that might distinguish it from the others. Each represents a different vision of what the invisible universe might contain. What strikes me is the creativity here, the willingness to imagine possibilities beyond our direct experience. We're trying to understand something we can't see, can't touch, can't detect directly. So we dream up particles, each one a different kind of ghost, and then we design experiments to catch them. It's speculation, yes, but informed speculation, constrained by mathematics, by observation, by everything we know about how the universe works. Some of these particles might exist, some might not. Some might exist but not be dark matter. The universe might contain all of them, or none of them, or something we haven't imagined yet. What we're really doing is mapping the space of possibilities, ruling things out, narrowing the options, learning what dark matter isn't even as we search for what it is. Each candidate is a different story about reality, a different answer to the question, what fills the darkness? And somewhere in these stories, or perhaps in a story we haven't written yet, the truth is waiting. Let's sit with an uncomfortable thought for a moment, a humble one. What if there is no dark matter? What if, after all this, the observations, the theories, the underground detectors, the particle candidates, we've been looking for something that doesn't exist? It's worth considering. Science progresses not just by being right, but by being willing to be wrong, to question our assumptions, to look at familiar evidence with fresh eyes. The evidence for dark matter is strong, galaxies rotating too fast, gravitational lensing, the cosmic web, the bullet cluster, all of it points to invisible mass. But what if we're misinterpreting what we see? There's an alternative idea, one that's been around almost as long as dark matter itself. Instead of inventing new matter to explain the observations, what if we've misunderstood gravity? What if gravity doesn't work quite the way Einstein described, especially at the enormous scales of galaxies and beyond? This idea goes by different names. MOND, Modified Newtonian Dynamics, is one of the earlier versions. The basic notion is simple. Maybe at very low accelerations, the kind you find at the edges of galaxies, gravity becomes stronger than Newton's or Einstein's equations predict. If that were true, you wouldn't need dark matter to explain rotation curves. Stars at the edge of galaxies move faster than expected, not because of invisible mass, but because gravity itself behaves differently out there. It's an appealing idea in some ways. Occam's razor suggests we shouldn't multiply entities unnecessarily. If we can explain observations by modifying our understanding of a force we already know exists, maybe that's simpler than inventing entirely new particles. And MOND does explain rotation curves remarkably well. Plug in the visible matter, apply the modified gravity formula, and the predictions match observations for many galaxies. But there are problems. MOND struggles with galaxy clusters. It doesn't explain gravitational lensing as naturally as dark matter does. And it has trouble with the cosmic microwave background, the faint radiation left over from the early universe. The patterns in that radiation match dark matter predictions beautifully. Then there's the bullet cluster again. Remember, the collision that separated the gas from the gravitational mass. Modified gravity theories have a hard time explaining how gravity could be in a different place from all the visible matter. Still, some physicists continue exploring modified gravity. Not MOND exactly, but more sophisticated theories. TeVs, emergent gravity, theories that try to bridge quantum mechanics and general relativity in ways that might naturally produce dark matter-like effects without dark matter itself. Maybe gravity emerges from deeper quantum phenomena we don't yet understand. Maybe what we call dark matter is really a manifestation of quantum entanglement at cosmic scales, or a thermodynamic property of space-time itself. These are speculative ideas, far from proven, but they remind us that our understanding is incomplete. We don't have a quantum theory of gravity yet. We don't know how to unite general relativity with quantum mechanics. Perhaps when we do, dark matter will make sense in a completely new way, or disappear entirely, explained by something deeper. There's also the possibility that both ideas are partially right. Maybe there is some dark matter, but less than we think, and gravity also works a bit differently at large scales. Nature doesn't always choose the simple answer. What I find valuable in all this is the uncertainty itself, the willingness to hold multiple possibilities at once, to say, we don't know without discomfort. Science isn't a collection of facts, it's a process, a conversation with the universe, and the universe doesn't always answer clearly. Sometimes it whispers, sometimes it seems to contradict itself. We do our best to listen, to interpret, knowing our understanding will evolve. Dark matter might be real, the most common substance in the universe filling space holding galaxies together, or it might be a placeholder, a name we've given to our confusion, destined to be replaced by deeper understanding. Either way, the mystery drives us forward. The not knowing becomes fuel for discovery. We're comfortable with questions here, with sitting in the space between certainty and ignorance, doing our best to map the darkness with the light we have. The universe will tell us eventually, or perhaps it will deepen the mystery further, reveal new layers we haven't imagined. We'll be here, watching, wondering, willing to be wrong if it means getting closer to truth. Let's return to the beginning, not just to the early clues or the first observations, but all the way back to the universe itself being born. 13.8 billion years ago, give or take, everything began. Space, time, energy, matter, all of it emerging from a hot, dense state we call the Big Bang. In those first moments, the universe was simple, mostly hydrogen and helium, radiation and energy, expanding and cooling, and dark matter already there, already present, woven into the fabric of existence from the start. We don't know where dark matter came from. Maybe it was created in the Big Bang alongside everything else. Maybe it emerged from processes we don't yet understand. But it was there, outnumbering ordinary matter 5-1, the way it still does today. As the universe expanded and cooled, something crucial happened. Dark matter began to clump. Remember, dark matter doesn't interact with radiation the way ordinary matter does. While hydrogen and helium were still too hot, still coupled to the intense light filling the early universe, dark matter was free to respond to gravity alone, so it fell together first. Slowly, over millions of years, dark matter gathered in the slightly denser regions, creating gravitational wells, depressions in space-time, and then, about 380,000 years after the Big Bang, the universe cooled enough for atoms to form. Electrons joined with nuclei. Light could finally travel freely. This is the moment we can still see. The cosmic microwave background, that faint glow from the early universe, now stretched and cooled by expansion. But more importantly for our story, ordinary matter was finally free to respond to gravity without being pushed apart by radiation, and it fell into the dark matter wells that had been forming, waiting. The first stars formed inside dark matter halos, small ones at first, scattered through space. These stars lived and died, creating heavier elements seeding the universe with carbon, oxygen, iron, the materials that would eventually become planets, and life. The first galaxies assembled where dark matter had concentrated most, not randomly scattered through space, but organized by dark matter's invisible architecture. Without dark matter, none of this would have happened, or at least not the way it did, not in time. Computer simulations show this clearly. Run a simulation of the universe without dark matter, and structure forms too slowly. By the time the universe reaches its current age, you'd have a much smoother, more uniform cosmos. Fewer galaxies, different structures, nothing like what we observe. Dark matter accelerated cosmic evolution. It provided the scaffolding, the gravitational seeds, the framework that allowed ordinary matter to gather and organize. Our own galaxy formed this way. 4.5 billion years ago, when the solar system condensed from a cloud of gas and dust, it did so within the Milky Way's dark matter halo. That halo was already ancient, already established, holding our galaxy together. The sun orbits through this halo now. We all do. Earth and everything on it moves through dark matter constantly. Think about that for a moment. Your origin story, not just as an individual, but as a species, as life itself, includes dark matter. The atoms in your body were forged in stars that formed in dark matter halos. The planet you stand on condensed from material organized by dark matter's gravity. You are, in a real sense, a product of dark matter's influence. Not directly. Dark matter didn't create you, but it created the conditions that made you possible. The structure, the organization, the gravitational stability that allowed stars to form, planets to coalesce, life to emerge and persist. We exist because the universe is structured, and the universe is structured because of dark matter. There's something profound in that connection. The invisible majority of the universe isn't separate from us, isn't irrelevant to our existence. It's foundational, intimate even. We are children of both kinds of matter, the ordinary atoms we're made from, and the dark matter that shaped their destiny. The universe needed both, light and dark, visible and invisible, working together across billions of years to create galaxies, stars, planets, life, consciousness. This very moment of quiet reflection. We're part of a larger story, one that begins with mystery and continues into mystery, but contains us nonetheless. The dark matter that filled the early universe still fills it now, still holds galaxies together, still shapes cosmic structure. And we're here, briefly, aware, looking back at our origins, trying to understand the invisible forces that made us possible. Let's drift outward now, away from galaxies, away from stars, into the spaces between, the voids. When we mapped the cosmic web earlier, we talked about filaments and clusters, the bright threads where galaxies gather. But we didn't linger in the empty spaces, the voids that make up most of the universe's volume. Let's go there now, into the darkness between. These aren't small gaps. We're talking about regions hundreds of millions of light years across, volumes so vast that our entire local group of galaxies, the Milky Way, Andromeda, and dozens of smaller companions, could fit inside with room to spare. And they're nearly empty, not completely. There are some galaxies scattered through the voids, isolated, lonely. But the density is incredibly low. If you were somehow standing in the middle of a cosmic void, looking around, you might see only a handful of galaxies in any direction. The rest would be darkness. Profound, encompassing darkness. No stars nearby, no nebulae, glowing. Just the distant light of galaxies at the void's edges, faint and far away. It sounds desolate, and in a way, it is. But these voids aren't failures of cosmic structure. They're part of the pattern, the negative space that defines the positive. You can't have filaments without voids, can't have density without emptiness, and the voids aren't truly empty. Dark matter is there. Less of it than in the filaments, yes, much less, but it's present, spread thin, a faint background of invisible matter permeating even these seemingly barren reaches. Remember, dark matter makes up most of the universe's mass. Even in the voids, where ordinary matter is scarce, dark matter provides a baseline, a subtle, gravitational presence. The voids are expanding. As the universe grows, the densest regions, the filaments and clusters, are actually pulling matter toward them, draining it from the voids. So the voids get emptier, larger, while the filaments get richer. It's a slow process, cosmic evolution on the grandest scale, the structure becoming more pronounced over billions of years. If you could watch a void over cosmic time, you'd see galaxies slowly drift toward its edges, pulled by the gravity of surrounding filaments, the void growing, the darkness deepening. There's a strange beauty to these empty places, a kind of cosmic silence. In a void, you'd be farther from other matter than anywhere else in the universe. the ultimate solitude. Light from the Big Bang would still reach you. The cosmic microwave background, that faint glow, would surround you as it does everywhere. But starlight would be rare. The night sky would be profoundly dark, and yet you wouldn't be alone. Dark matter would be there, invisible companion in the emptiness. Particles streaming past unnoticed, unfelt but present. It makes you wonder what dark matter experiences, if that word even applies. Does it notice the difference between a dense galaxy and an empty void? Probably not. It moves through both with equal indifference, barely interacting with anything. From dark matter's perspective, if it has one, the universe might seem uniform. No bright stars to avoid, no dense planets to navigate around. Just gravity, space-time's curvature, the slow drift of cosmic expansion. The voids remind us that most of the universe is empty. Not empty of dark matter, but empty of us. Of stars and light, and the phenomena we associate with existence. We live in the bright places, the dense places, the exceptional corners where matter has gathered enough to ignite, to shine, to create complexity. But the voids are the norm, the baseline, the cosmic default. And even there, in that profound emptiness, dark matter maintains its patient presence. Not clustered, not structured, just spread thin like mist, filling space that would otherwise contain almost nothing. There's something humbling about that. The universe doesn't need us, doesn't need stars or galaxies. Most of it is void, and it's fine with that. Indifferent, vast. We're guests in the bright corners, temporary patterns in the darkness, but we're here, and for now, that's enough. The voids will continue expanding. The darkness between will deepen, and dark matter will fill it, quietly, invisibly, as it always has, marking the emptiness with its subtle gravity, proving that even nothing contains something we cannot see. Come back with me now, back from the cosmic voids, back from the distant filaments and clusters, back through space, back to our galaxy, our solar system, our planet, back to where you are right now. Here's something remarkable. Dark matter is passing through you. Right now, as you rest, as you breathe, particles of dark matter, if they are particles, are streaming through your body, through the room around you, through the earth beneath you. Billions of them every second. They enter through your head, pass through your brain, your heart, your bones, and exit through your feet without slowing down, without noticing you're there, without leaving any trace. You're transparent to dark matter, as transparent as empty space. The Earth is transparent too. Dark matter flows through our entire planet as if it were made of nothing. The iron core, the rocky mantle, the oceans, the atmosphere, none of it matters. None of it stops or slows the dark matter stream. We're immersed in it, swimming in an invisible ocean that we can't feel, can't touch, can't detect except through its gravitational effects on the larger scales. Think about that for a moment. Your experience of reality is fundamentally incomplete. Most of the universe's mass surrounds you, fills you, moves through you constantly, and you have no sensory awareness of it whatsoever. It's not a failure of your senses. Your eyes evolved to see light, your ears to hear sound waves in air, your skin to feel pressure and temperature. These senses tell you about ordinary matter, and they do it beautifully. But dark matter doesn't interact with light, doesn't push air, doesn't create pressure. Your senses were never meant to detect it, so it remains invisible, present but imperceptible. The dark matter particles passing through you right now might have travelled across the galaxy. They might have orbited the Milky Way's centre dozens of times, cycling through the halo, passing through stars and planets, and nebulae without ever interacting. They've been doing this for billions of years, long before Earth existed, long before the Sun formed, and they'll continue long after we're gone. Patient travellers through space-time, barely aware that ordinary matter exists at all. There's something oddly comforting about this. We worry about so many things: our bodies, our safety, our space. We feel solid, bounded, separate. But dark matter reminds us we're permeable, open, part of a larger universe that moves through us as much as we move through it. You're not separate from the cosmos. You are embedded in it, made of matter that was once in stars, breathing air that cycles through all living things and constantly being passed through by the universe's dark majority. It changes nothing about your daily life. You'll wake up tomorrow the same person, with the same concerns, the same routines. But maybe, occasionally you'll remember. You'll think, right now, in this moment, I'm part of something vast, something mostly invisible, something that fills space and time and holds galaxies together. Dark matter doesn't care about you, doesn't notice you, but you can notice it. You can know it's there, even if you can't feel it. And there's a strange intimacy in that knowledge. The universe's greatest mystery isn't distant. It's here, closer than your breath, closer than your skin. You live in a dark universe. We all do. And now you know. We've travelled far together, through observations and theories, through underground laboratories and cosmic voids, through the history of discovery and the uncertainty that remains. And after all of it, we still don't know what dark matter is. We don't know if it's particles or something else entirely. We don't know if we'll ever detect it directly. We might be on the verge of understanding, or we might be missing something fundamental about how the universe works. We don't know, and you know what? That's okay. There's something beautiful about mystery, about standing at the edge of human knowledge and looking out into what we haven't yet understood. We live in an age where information feels infinite, where we can search for any fact, find any answer, learn about almost anything with a few touches on a screen. It's easy to forget that there are still things we genuinely don't know, real mysteries, deep ones. Dark matter is one of them. It's not a mystery like a detective story, where all the clues are already present and we just need to piece them together. It's deeper than that. We might be missing fundamental clues. We might need entirely new ways of thinking, new mathematics, new instruments, new insights that haven't occurred to anyone yet. The universe doesn't owe us answers. It doesn't simplify itself for our convenience. It is what it is, vast and complex and strange, and we're doing our best to understand it with the tools we have. Sometimes those tools aren't enough yet. Sometimes we have to sit with not knowing, and there's a kind of peace in that, a humility. Think about all the scientists we've mentioned, Zwicky, Rubin, the teams building detectors underground, the theorists proposing new particles. They've dedicated their lives to this mystery. Some have spent entire careers searching for dark matter without finding it. That's not failure. That's devotion. That's being willing to live with questions, to pursue understanding even when answers don't come easily. They're teaching us something important, that the search itself has value, that mystery is not something to be feared or avoided, but something to be honoured, explored, sat with patiently. The universe is still surprising us, still showing us that reality is stranger and more layered than we imagined. Isn't that wonderful? We could live in a universe that was simple, fully understood, mapped completely, where every question had an answer, where nothing remained hidden. But we don't. We live in a universe that's mostly invisible, where the majority of matter reveals itself only through gravity, where the cosmos is structured by something we can't see, can't touch, can't fully explain yet. We live in a universe that still has room for wonder. Dark matter keeps us humble, keeps us curious, keeps us looking up at the night sky and out at the cosmos with genuine awe, knowing that what we see is just a fraction of what's there. Mystery is a gift. It means there's still more to discover, still more to learn, still frontiers ahead of us, still questions worth asking. And maybe someday we'll understand dark matter completely. Maybe we'll detect the particles, or revolutionize our understanding of gravity, or discover something we haven't imagined yet. Or maybe the mystery will deepen. Maybe we'll find that dark matter is even stranger than we thought. Maybe it will lead us to new mysteries, new questions, new horizons of understanding. Either way, we'll keep looking, keep wondering, keep sitting with the questions, patient and curious, because that's what it means to be human, to stand in the darkness, unable to see everything, and still reach out with wonder toward what we cannot yet grasp. The universe is dark, and that darkness is beautiful. We've come to the end of our journey together. But really, there is no end. The universe continues, the dark matter continues, the mystery remains, patient and vast. You can rest now, or stay awake, thinking, wondering. Either way is fine. The cosmos doesn't mind. Let's settle into this moment, into the darkness around you, the quiet, the stillness. You know now that darkness isn't empty. It never was. It's full of invisible matter, full of structure, full of the gravitational threads that hold everything together. The night sky above you, whether you can see it or not, is filled with galaxies, and those galaxies are held by dark matter halos, cradled in invisible embrace. The space between stars isn't vacant. Dark matter drifts there. The space around you, this room, your body. Dark matter passes through constantly, a silent river you'll never feel. You are part of this, not separate from the cosmic mystery, but woven into it, made of atoms that formed in the gravitational wells dark matter created, living on a planet that orbits through a dark matter halo, breathing, thinking, existing in a universe that is mostly invisible. And that's okay. You don't need to understand everything to be part of it. You don't need to solve every mystery to rest peacefully in the darkness. The universe has been here for almost 14 billion years. It will be here long after we're gone. Dark matter will continue its patient presence, holding galaxies, shaping structure, filling the voids. It doesn't need our understanding. But we reach toward it anyway, because that's what we do. We wonder, we question, we explore. And sometimes, like now, we simply rest. We let the mystery be mysterious. We accept that some things remain hidden, that darkness is real, that the universe is deeper than we can fully grasp. There's comfort in that, in knowing you're part of something larger, something that doesn't depend on you but includes you nonetheless. So rest. Now, if you'd like, let your thoughts drift. Let the darkness hold you the way dark matter holds the galaxies, invisibly, gently, with a gravity you don't need to feel to know it's there. We've travelled far together tonight, through time, through space, through the history of discovery and the frontiers of mystery. Thank you for coming along. Thank you for wondering with me. If these cosmic explorations resonated with you, if they brought you some peace or sparked some curiosity, consider subscribing. There are more mysteries to explore, more quiet journeys through space and time. We'll be here, waiting in the darkness, whenever you'd like to return. But for now, rest. The universe continues without hurry. The dark matter flows, the galaxies spin, the cosmic web stretches across billions of light years, and you are here, part of it all, held by invisible forces, surrounded by mystery, safe in the darkness, safe in the not knowing, safe in the vast patient universe that made you possible. Sleep well, if sleep finds you, or stay awake, thinking about the invisible ocean you're swimming through. Either way, you're exactly where you need to be, in the darkness, in the mystery, in the universe that is mostly hidden, mostly unknown, and entirely, completely real. Good night.